Hello, on behalf of TeamRNH, I present to you a low-cost wireless satellite hub which provides optimum performance. For every engineering problem, we have to deal with some trade-offs. These are the few design constraints and assumptions we have taken into consideration for this project. The device has a separate command line on which it sends to the hub a command signal that contains the device ID, data tag, data size, read and write command. The device can either request or send data from or to the hub at a time. However, it cannot do both simultaneously. Any data sent to the hub by the device is directly sent to the data center in case the memory is found to be full. We have had to utilize part of the 256-byte memory for storing memory address, tag, and valid bits. After a survey of the provided test cases, we could infer that the request for reading and writing the data of transaction size 512 bytes was minimum, that for 128 bytes was second popular, and that for 1 kilobyte was most frequent. In an attempt to ensure minimum unit cost coupled with minimum communication cost, we have made the following decisions regarding the memory architecture. Our hub is divided into 6 blocks of memories. One memory of type M1, 2 memories of type M2, 7 memories of type M3. The memory M1 has a capacity of 256 bytes. The memory M2 has a capacity of 512 bytes, and the memory M3 has a capacity of 1 kilobyte. Apart from these 3 memories, we have made use of 6 16-bit buffers to implement a request queue.
Memory M1 has 256 bytes divided as upper 128 bytes into tag address memory and a valid bit memory, and a lower byte of 128 bytes. The tag memory is divided into memory address of 5 bits, tag of 5 bits, data size of 2 bits, and redundant 4 bits. The data size of 2 bits is used to address 128 bytes, 512, 1024 bytes, and a size of 111 says it's illegal. Also, the valid bits per memory in M1 are divided according to row 27 and 28. The bits indicate if the memory corresponding to the particular address is empty or not. For a value of V, if it is 0, it's an empty location. If it is 1, it is a filled slot. For value of enable and enable 1 and 2, 1, if the slots are filled, 0, it is empty. The M2 memory architecture is divided into 5 and 2 bytes M2BA and 5 and 2 bytes M2BA. The one memory is sectored into 4 slots to correspond to 128 bytes of data, and another memory is dedicated for 5 and 2 bytes. The M3 architecture consists of 21024 bytes of memory and 51024 bytes of memory. 2 memories are sectored into 8 slots of 128 bytes to accommodate the data chunk, and there are 5 memories dedicated for 1 KB of data. Modules consist of a scheduler, which is a 16-bit buffer to store sequence of device requests lined up for the incoming device connection. It implements a simple FIFO. There is an address decoder which returns a memory address value, having a read operation and a write operation. Controllers decides which module to invoke depending upon the memory address value received. The memory modules are M1, M2, and M3, which performs read and write operations. Overall design flow of the architecture is whenever device sends a request or it sends to a scheduler then forwards it to a controller. Controller transfers the signal to address decoder, and address decoder gives a memory address value to the controller. The controller then controls memory M1, M2, M3 according to the read-write operations. Controller design flow is as follows. If there is a device request, it will read the data. If the address or else the address module will be enabled 1. The processor readout is if it is yes, then it will go and decode if an address is 0. If for memory address 1, it is 1 to 4 or 26, and for memory address 3, it is address 5 to 25. And if the busy signals are 0 or 1, it is encoded into an AND gate and it is given to the device request again. An address decoder, it is used to for the address decoder. If there is a read request, it will compare the tags and accordingly the memory will be selected. If no, then the output will be set high to 111. If it is not a read request, then it is a write request. The sizes of the memory will be compared, the valids bit will be compared, and the output is given to the memory. Regarding test cases and benchmarks, the total unit cost was $91. Communicative latency, as shown in the slide, for an M1 memory was 18496 clock cycles, and these are our cumulative results for latency and communication cost. For our future enhancements, parallel processing of data request and send for the same device, also receiving and sending a serial data from to and fro to a device while executing another request in parallel, and an eviction strategy. Thank you.